Dr. Corbin's gonna escort you out of the building.
Okay, so up to this point, guys, we've been talking about gases at a macroscopic level. Okay. Hey, it's time to listen. So we've been talking about, like, if I have a whole gas sample, the pressure, the volume, the temperature of that gas sample. We're just going to tie up some loose ends today and talk about the behavior of gas particles, the individual particles, and how different things affect those things. I'm going to start with kinetic molecular theory because that's something we need to cover for this class. This is basically just an explanation of how gases behave and why they behave the way they do. And I'm telling you it because we've already talked about some of these concepts, and it was developed like 200 years ago, and it turns out it's still true. So the hypothesis that they proposed back in the day, hey, we were right, okay? You don't necessarily need to write this down, but there's basically 4 statements here that are kind of just summarizing what we have discussed so far, okay? I am not going to ask you to like memorize these and write them down on the test, but they are concepts you need to know, okay? Once I show them to you, most of them are gonna be like, oh yeah, duh, I already know that, okay? So it's kind of just a summary, okay? So the first thing is we know that gas samples are composed of particles that are just moving around randomly, okay? There's not necessarily a pattern to how gas particles move, okay? The phrase that we usually commonly use is they just kind of bounce around, okay? So then the other thing about that is that even though, if we look back on the back shelf up there, there's balloons up there. Those balloons are a pretty decent size. Anyone remember the volume of the balloons that you were trying to get to? How many liters are those balloons?
Yeah.
Based on your calculations?
24.2.
24 liters, roughly. But if I were to take all the gas particles in those balloons and pull them all together, any idea how much space the particles by themselves take up?
Not a lot.
About a drop, like a drop or less. So a tiny amount of space. So the balloon is like this big, but the particles, if they were all packed together, would take up less space than a drop of water. So then what's all the other space? Well, it's literally just that, it's just space. Okay, so the particles are very spread out relative to their size, okay?
Bless you.
Another thing we talked about is that although I kind of mentioned this, there may or may not be attractive forces between the particles or repelling forces, and that actually is a thing. You don't have to worry about it unless you go to college and become a chem major. In upper level chemistry, you have to worry about that. But for our classes, we don't have to worry about that, and that's because even with these forces of interactions between gas particles, we can ignore them. Okay, and so this specifically factored into what we talked about partial pressure. If I have a mixture of gases in a container, I don't have to care about what types of gases are in my mixture. I can just add the 2 pressures together and they don't really affect each other in that way. Okay, so that was a nice thing about that. And then the last thing we have is that gas pressure is caused by the particles literally just whacking into the inside of the container. It's pushing it out, right? So the only reason that those balloons back there are this big is because the particles are going so fast, they're literally pushing the balloon out and keeping it inflated, because we know the balloon is stretchy, it wants to collapse, but the gas particles are continually pushing it out and keeping it inflated. Okay, so gas pressure is caused by the particles bouncing around and pushing the container outward. Okay, so these are just kind of our 4 statements that kind of summarize how gases behave. Okay, I'll give you a few seconds to make some notes of that if you want. And then I have a gift to show you. Can't remember what it stands for. I just know the G stands for graphic. Graphic something. GIF.
What about Jeff?
Well, see, I don't say GIF. A, that's peanut butter. B, the G stands for graphic, so that's why I say GIF, because the word that GIF stands for is graphic. I just can't remember the rest of it. 3, 2, 1, go.
Go. Wow.
Hey, look, it's a gas.
Interesting.
Someone has to go back 1 sec. Yes.
What are the red particles?
Good question. So on the next slide, I have red and blue. The red particles are there just so you can easily follow a particle if you want to track it, okay? Because sometimes the blue ones, they get easy to get mixed up, okay? So I got these particles. What do we notice about
Well, that's hard.
these particles and how they're moving? Some observations, interesting or not interesting observations?
It seems to be random.
Seems to be random.
They're hitting off each other.
They're bouncing off each other. Yes.
The more they bounce off of each other, the more they go everywhere.
Okay. What else?
There's red ones and blue ones.
There's red ones and blue ones. Okay. Anything else?
More blue, less red.
Okay.
They're inside a box.
They're in a box.
They're kind of going slow, but one of them hits them really fast.
Oh, I like that. So they're going slow until something hits it.
Isn't that like one of the
So yeah. So here's some other questions. Are all the particles going the same speed?
No.
Clearly not. Is one individual particle going at consistent speed, or do they change speed?
They change.
Okay, so we're gonna dig into this a little more, okay? So this is a question I wanna answer today. What factors will affect the motion of these particles?
Getting smacked.
Okay, so for example, if I were to change things about my sample here, would that affect how they move? So for example, if I changed the temperature of this, do you think that would affect how they move around?
Slower, right? Volume.
Could. If I were to change the size of my container, do you think that might affect how they move, or do you think it would just be the same? Or what if I changed the pressure? Or what if I had heavy gas particles versus lightweight gas particles?
Definitely.
I'm kind of just spamming through some questions here. In fifth hour, we had a disagreement. Some people said if I expand the container, they would move slower. And then someone said if I expand it, it wouldn't make a difference. They would move the same way. They just have more space.
No, because I think it would go slower because they're hitting off the wall and going fast and hitting the other ones.
Okay.
They're like going slow.
Okay.
If you
Mr.
don't
Floyd,
hit
Without the collisions. Josh?
let's say the way it's at right now, it's like 10 psi, and when you make it bigger, the pressure's gonna reduce, so it doesn't mean the gas particles move slower, and they're not crazy.
Could be. Or maybe it could be that. So that's kind of changing two things at once. If I increase volume and decrease pressure, maybe that would affect their speed. It might not. So we're gonna dig into this, okay? Also, there's a little caption here from the website. This is a simulation of helium atoms at 1950 atmospheres, 1,950 atmospheres.
Whoa.
This is also in super slow motion. The particles are moving trillions of times faster than this in real life at that pressure.
Read
Yeah.
that up for me.
Okay, so this is super slow mo. It looks pretty speedy as is, but this is super slow mo.
Wow.
Kind of interesting. Okay, so here we go. Let's start with kinetic energy. Okay, there's two things that we're going to look at today: how fast the particles move and the energy that they have. Okay, so the first thing we'll look at is average kinetic energy. Okay, and actually, I probably should reword this. It should be like the particles plural in a sample, right? Because average means I'm looking at the whole thing. Throwback to physical science. What does kinetic energy mean?
The energy inside of something?
Sorta, not really.
Potential energy? Is that what it is?
It's the energy that has to do with, what'd you say, Jackson?
Movement?
Yeah, movement. Okay. So this is the energy that particles have when they're moving, right? So if I have this racquetball and it's moving, it has kinetic energy because it's in motion. Okay, great.
But if it's sitting there, it doesn't have potential.
Very nice. Okay, so some things we might ask. If I were to change the pressure, guys, if I were to change the pressure of my gas, would the average kinetic energy, would the motion of the particles change? Or the volume, the temperature, the mass, okay? These are the questions we were just talking about, okay? So what we're gonna do is I'm gonna show you an equation, or we're gonna actually figure out the equation that describes average kinetic energy. And what I want us to notice over here is what variables are on this side, because the variables on this side are what determine or what affect the kinetic energy. If one of these variables does not show up in the equation, then that means it has no effect on the energy, okay? So This equation will answer these questions, whether or not these are relevant or not. Okay, now because this is kind of a college class, I'm gonna not only just show you the equation, I'm gonna show you where it comes from. Okay, so here we go. Let's start simple. Another throwback to physical science. What's the equation for kinetic energy?
Something true. The change of something over the change of something.
There's no delta.
Oh golly.
It's some number mixed with some other.
Give us the hint. Give us.
Well, you could probably figure it out. So this is moving, yes, it has energy. If it's moving faster, it has more energy.
Velocity?
Velocity is one thing that affects
Mass.
it, right?
Mass?
That's literally both. So if it moves from here to here, well, I don't know. What distance affect it?
Time.
Is how far it moves determine how much energy?
You're the
Sure.
teacher. Come on.
Oh, wrong arrow.
Is it MCAT?
Mass.
No, that's the heat. That's the heat one. That's heat energy. M stands for mass. U stands for speed.
What?
U stands for speed. I don't know. It just does.
You.
No, U, not mu.
U is a Greek letter.
It is. Although that looks like a mu.
You.
Okay. Now, this is how we can calculate kinetic energy for macroscopic particles. It should work for gas particles. The problem is, guys, the problem with this equation, like you found with the balloon, is just because I have an equation doesn't mean I can apply it. Okay, can I measure the mass of individual gas particles?
No.
Not really. I mean, we have molar mass, which kind of helps, okay? But what about, can I measure the speed of individual gas particles?
They're moving too fast.
They're moving too fast and they're too tiny. I don't have a speed gun that small, right? Okay, so this is like true, but it's not helpful. So let's try to rearrange this and put it in terms of things that we can actually measure for a gas, okay? And in order to do that, I'm gonna bring in another equation. Okay, this is another one. I'm not necessarily gonna show you where it came from. Okay.
Do you need to know it, or?
No. So this is now where I'm gonna take this and this, and we're gonna do some math magic and make a new equation.
Like substitution or something?
Yes, we're gonna do substitution stuff. I'm going to show you where the equation on the next board comes from. The next slide comes from. Okay, and these are my two starting points. Okay, so we know what kinetic energy is as a concept. This is an equation that represents pressure, and we can derive this from laws of physics. I'm not going to show where it comes from. You can see my book if you want to look it up yourself. But this kind of makes sense, though. Okay, so let's notice. N stands for the number of particles. Okay, M is mass, U is speed, V is
Velocity.
volume.
Oh.
Okay. Okay, so if we're looking at this equation, okay, concepts. Don't write this down. I just want you to think about these concepts, okay? N over V, number of particles per unit volume, is kind of like density, yes? Right? How many particles do I have in a certain space? Yeah? And if this is part of my pressure equation, it makes sense that if I had more particles, there'd be more pressure because I have more stuff packed into a certain space, right? Or if I decrease the volume or increase the volume, that would affect how much pressure there is, right? How packed in they are together, okay? So it makes sense that N and V is in there, okay? U represents the speed of the gas particles. Does it also make sense that if I increase the speed or decrease the speed of the particles, that would have an effect on pressure? Okay, I'm just trying to like get us, like, this is not just gibberish per se. It does, but it makes sense why these things are in here. Okay, all right. That's really all I wanted to say with that. Okay, so we got these two things. We're trying to find an equation for this in terms of things that we can measure. Okay, this is true, but these are not useful things for me, for gases. Okay, so notice how both of these equations have mu squared in them. Yes? So that means if I wanted to, if I felt like it, I could solve both of these for mu squared. Yes? 3pv over n. Did I do that right?
Yeah.
Okay. So I just felt like doing that just because I did. But hey, look, A equals B, B equals C.
A equals C. A squared plus B squared equals C.
This
A
happened in
equals
fifth.
C.
I love how when I start saying things, people just start randomly saying things.
Well, you look like you're looking for something that we know.
No,
That's
I
not it.
lit.
It's equal to
Right. If this and this both equal the same thing, what do I know about these two things? They equal each other. There you go. Okay, so check it out.
Basically, C squared.
I know I could say that energy equals that, right? So I had 2E equals 3PV over N, right? That's that and that. And then I can put the
It's
2
not
down
what we
here.
need to write down.
Not yet.
Bruh.
I will tell you.
Well,
I'm getting somewhere.
you're really working me up right now.
Okay.
Whoa.
You just need to, it's movie time. Just enjoy the show,
I've been
okay?
exploded since first hour.
You don't need to take any notes right now. Okay. So energy also equals 3PV or 2N, yes? Do you believe me? And I proved it to you because math? Okay. Now, I don't like that N is here because it's hard to count the exact number of particles in my sample, right? You guys kind of estimated the particles in that balloon, but you can only count like to the nearest like quintillion or something, okay? But this is like the exact number, okay? Well, maybe we can do some more math magic and get rid of N, okay? Well, we also know that, hey look, PV. I have another equation that has PV. So if PV, so so I have PV here. If PV equals NERT, can't I take NERT and plug it in for PIV?
And then can you cancel the and?
So now, look, I just put NERT in for PIV.
Can you cancel the
Almost.
Almost.
Almost. It's different. I'm on the edge of my seat, bro.
Okay. This is the number of particles.
Uh-huh.
What is lowercase n?
Number of
The moles. So this is the number of particles, individual atoms. This is how many particles there are, but in groups of moles. Okay, well, another equation that we talked about before is that moles is by just taking the number of particles I have over Avogadro's number. We talked about this a couple weeks ago, okay? Well, hold on. Yeah, check it out. N over N equals,
Does this work? This means you gotta
yes, I can rearrange that. And then I can take N over N and replace it over here.
Oh my golly.
Wait,
I'm drowning. Is that the end?
where'd it go?
Yes, it is the end. Josh.
So what's the,
Oh,
so the mole is equal to,
This is moles, yes, is the number of particles grouped by Avogadro's number.
so you have the number of particles to the number of particles times Avogadro's number?
No, this whole thing is Avogadro's number.
Okay.
It's just labeled with an A.
Avogadro's number.
Yes, Zoe?
You're giving us Avogadro's number?
No, you
We
need to
have
memorize
to-
it.
What?
Wait, I thought you said you were giving us.
Yeah.
Isn't that like
You're
six?
giving
You're
us
not
that
listening.
one and then
I'm
another
giving you the
constant.
gas constants. I'm not giving you Avogadro's number.
Okay, you time out. So Avogadro's number
Is
is A.
Avogadro's number? Is
Let's
it
put
yeah, what is that? Oh, is it the moles?
10 to the 23.
Oh, that's what that is?
That's
Atoms.
We have to remember that.
Avogadro's number.
Yes, Leo.
Okay, can you like, on that final equation, can you like label what each of those?
I'm about to. I'm about to.
It just kind of looks like random.
Okay. Do we have other questions?
That will be fine.
Do we have to remember this equation?
The one at the bottom, yes, is the one you need to know.
Okay.
I'll commit this to memory. 2 days.
I'll let you write it down and then we're gonna talk about it.
R. Where did we get R?
It came from NERT.
Aaliyah.
You have too much faith in me.
What?
Well, your academic history is gonna be pretty good. Actually, my paper, I can tell. But you can turn that in for me.
Okay.
So I don't wanna hear that.
Everyone come back in. I let you write things down. Now look. Notice what happened, okay? This was all one slide, but it was quite the journey, okay? We know what kinetic energy is. Mass times velocity squared divided by 2. Okay. The whole point of this slide is I want to be able to calculate, Lydia, I want to be able to calculate the
Killer.
Kinetic energy. Kinetic mole.
I'm waiting for people to listen. Okay. I wanted to be able to calculate the kinetic energy, or at least the average kinetic energy of my gas particles. This equation is true, but it's not helpful because we have mass and speed, two things I can't measure for gas particles. Okay, I brought in another equation and we did a substitution, and then we did a substitution, and then we did a substitution. We just did 3 switching things around. Now let's analyze what we ended up with. Okay, the kinetic energy, or the average kinetic energy of my particles, depends on these things. Now it looks like a big mess, but you'll notice it's actually not that many things.
Temperature.
Temperature is the only thing that I can adjust. Is 3 something I can adjust?
No.
It's just a number, okay? Is R something I can adjust? It's just a constant. Okay, so depending on my units, it's just, yeah.
So it's just.
And then 2 is a constant. Avogadro's number is a constant. Okay? So, check it out. Here's the takeaway. The only thing that affects kinetic energy is
Temperature.
the temperature. Does the volume of my container matter?
No.
Does the pressure matter?
No.
Does the type of gas matter? No. The temperature is the only thing that affects the average kinetic energy of my particles.
Well, that makes sense though, because like if you think about it, like temperature affects like the physical state.
Sure.
If you heat it up, the atoms heat up. That's how you get solid liquids.
But here's the interesting thing is, yes, if I heat it up, they do move faster. It's interesting to me that I could have heavy and lightweight atoms, and we're going to talk about how in a second the speeds, they can move at different speeds, but the big ones move slower and the small ones move faster. So even if I have atoms of different sizes with different speeds, the energy will work out to be the same if I keep them at the same temperature, which is kind of interesting. I feel like I should do the speed first and do this after. But anyway, okay, so even with different sizes of atoms moving at different speeds, notice how speed is not necessarily in here, the energy is the same, okay, the average energy.
So, to define like the kinetic or whatever it is,
Yeah.
you just need temperature.
The average kinetic energy, yeah, literally just the temperature. Nothing else matters. Kind of interesting. Okay, questions about this?
What makes some big and some little?
The type of atom it is,
Okay.
right? Like the mass.
Can we do like an example?
Yes. Let me do one other thing and then there will be examples. We'll probably do examples tomorrow, but it will happen. Okay. Da-da-da, da-da-da. You can go read that later. Okay. So, next thing. We kind of already looked at this, but I just have all of these fun little simulators. Hey, look, it's gas.
I guess.
What is this? What is this simulator telling us? Hey, it's the speed of the gas molecules. Are we observing anything the same or different about the? So we looked at that GIF earlier. Are there different things to observe, or are they kind of doing the same thing?
Same when they collide.
Are all the particles moving the same speed?
No.
Are individual particles moving at a consistent speed?
No.
No, individual particles are changing speed and they're all at different speeds. So it seems just like random chaos. But there's actually something here that is the same. Now, if I click down here, I can turn on a little calculator that calculates the average speed in real time, right? So you'll notice these numbers here are plugged in at the top and it calculates the average in real time. So here's the average speed. What do we notice about the average? Is it consistent?
No.
It's not consistent. It also changes. It's staying within, like, you know, it's in the 90s. So it's somewhat consistent. Okay, so interesting. Now there's another type of average that doesn't really come up in other classes, but I'm bringing it up because it's important for this. There's another type of average called root mean square. So mean is just that. Root mean square is a different type of average. It's a different equation. You don't necessarily need to worry about it. But when I turn that on, we can see it will calculate that. Okay, so here's a different equation. It's a different type of average. What do we notice about the root mean square?
It's constant.
Yeah, interesting. So even though these particles are changing speed all the time, and they're not all the same speed, the average speed, or this particular type of average versus that average, this average is always the same.
Does it ever change?
Ow.
It will, well, it might change if I change some other things. So the next thing we want to look at is, well, what affects the average speed? Does the temperature, the pressure, the volume, the type of gas, what affects that? Okay, so that's the next thing we're going to look at, then we're done. Okay, Levi?
So, like thinking backwards, does that mean like you can tell what the temperature is, like if you're given like the kinetic energy?
From the last equation, sure. The average kinetic energy, yeah, you could just calculate backwards.
How
Yeah.
does the root mean thing work?
So the way this technically works is you take every speed, you square them individually, add them up, divide by how many there are, and then take the square root of all that. Okay? It's just a different way of taking an average. You will not need to do this, which is why I'm kind of glazing over it. Okay? It's just a different type of average. Okay?
Is that gonna be like anything on the test, or do you just want like?
Let me show you.
Okay.
Okay?
Yeah,
So,
it shows the test.
without proving it to you, this is how we can calculate the root mean speed of gas particles. Okay? Please write this one down. Okay, so the thing from the simulator is how you can calculate it. For gases, you can calculate it this way. 3RT over capital M.
It's capital.
What is capital M?
Is that molar?
Molar mass. Yeah.
All under the square root.
What does T stand for?
Temperature.
Temperature. What does R stand for? What does 3 stand? Never mind. Okay, so there you go. There's your key. R is the gas constant, T is the temperature, and M is the molar mass. Okay, so I'm not going to do anything to this equation. This is the equation we're going to use. Notice, so now, let's think like a scientist. What things affect the average speed of my gas particles based on that equation? The temperature, anything else? The molar mass, which translates to the type of gas that I'm dealing with,
What?
right? Is it helium? Is it neon? Is it krypton? Those all have different masses, and so it's basically telling us the type of gas matters because they weigh different amounts. They have different masses. Okay, now, so that was thinking like, that's thinking like scientists, thinking like a mathematician, right? We know that anything over here is going to be affecting this. That's what this is. It's a math, it's a sentence in math. Okay, we're just translating it. Now, another way we can think like a mathematician is we automatically think about, well, what if I change things? How do they interact? If I were to change temperature, a mathematician looks at this and goes, ah, that's in the numerator. So that means it's directly proportional to this. So if I increase the temperature, what happens to my average speed?
It increases.
And if I decrease the temperature, decrease speed. That's directly proportional, right? Mathematician looks at that and goes, ah, that's on the denominator. So that means that this is indirectly proportional to speed. If I have heavier particles, increased mass, what happens to my average speed? And then if I have lighter particles, less mass, higher speed, which kind of makes sense. Heavy particles move slower, lightweight particles move faster. It's intuitive, right? It works the same way with large objects. Okay. Okay. Okay, so I want us to keep in mind. Okay, what I just showed you. Okay, the U is the average speed. Okay, so I'm not saying that all the particles move at the same speed. We've seen multiple little simulators here. The individual particles are moving at different speeds, and their individual speeds are changing. But the average will always stay the same. So even though all those particles are changing what they're doing, the average doesn't change, unless I change the temperature or something like that. Okay. All right. Now, last slide. Let's look at what happens if I do change the temperature or the mass. Notice what's going on. Let me write these in bigger. Listen to me explain it, and then you can decide what to write down. Okay, let's compare these two first. Okay, these two red graphs. Okay, what is this graph telling us about? O2. What are on my axes? Temperature this way. Average speed. Yep. Just says speed. So yeah, you're right. But it's actually no, it is speed. I'm sorry. And then so this is showing all of the gas particles. No, this is not the temperature. What is this? Can you guys see this?
No.
Number of particles. The different graphs are at different temperatures, but this axis is number of particles, okay? So notice what's going on. At a certain temperature, lots of particles are going about, so the average is like right here, so that's U is right there. A lot of particles are going about the average speed, but some particles are going how fast? Not moving, but only a couple of them. But similarly, over on here, a few particles are going super duper fast, right? Most are in the middle, but some are outliers on either side. Okay, well, great. Well, what if I increase the temperature of my oxygen? What do we notice about these two different graphs? It gets wider, so my range of speeds is wider. So the first graph had this range, whereas the other one has that range. Okay, so I have some particles, so my maximum speed is increased. And then notice my average, so my average is about right there. My average did move, right? It moved over about a little bit. Okay, but I have a wider distribution of speeds. Okay, interesting.
How hot is 1,000 Kelvin?
That is hundreds of degrees Fahrenheit. That's like at 700 Celsius, which is gonna be, it's like 400 Fahrenheit roughly, ballpark. It's pretty hot, pretty hot. Well, it's like your oven, so your oven, I don't know, 1,000 Kelvin.
Just make some cookies.
Yeah, just bake some cookies. Okay, so now let's compare this one and this one, okay? So this is O2 at 273. This is H2 at 273. Same temperature, different type of gas. What about those gases is different besides the type?
O2 big.
It's heavier, yeah. So it is bigger, but it's also heavier. These are heavy particles. These are very lightweight particles. What do we notice about the speeds?
Hydrogen has bigger.
Hydrogen can go way faster. Is its average higher as well?
Yeah.
Yes, the average is higher as well. But they're the same temperature. How can these go faster if they're the same temperature?
Because mass of
They're less, right, they have different masses. Okay. Also, just to give us an appreciation for this, okay, do we see how fast these particles are moving?
Those are meters a second.
Meters per second, 1,000, 2,000, 3,000, 4,000. Okay, this is thousands of meters per second, which is also thousands of miles per hour. Okay, I can't remember, I've made a little note. 1,000 meters per second is 2,000 miles per hour. So 2,000 miles an hour, 4,000 miles an hour, 6,000 miles an hour. And that's at freezing, right? That's cold. So at room temperature, so everyone pause and think about this and then we'll be done. In this room, there's oxygen, yes?
Yes.
And according to this graph, There are oxygen molecules flying around this room at thousands of miles an hour, and they're hitting you in the face and all over. But they're so tiny you don't even notice it. But gas particles are moving extremely fast. Okay? Yes?
How come we don't feel it bouncing against ourselves?
We don't have the nerves to detect it. I don't know, our bodies aren't equipped to detect it.
That's nice.
Yeah, I guess so.
Feel 1,000
No,
of them.
1,000.
All of
Death
us
by
are
1,000.
actually,
It's
like,
like death by a. I know. Bunch of paper cuts. Or punches. Say you're getting punched 1,000,000 times, just micro size. Okay, questions? Later.